introduction, Robin. This is Steve Hudak. I'm going to go ahead and lead the presentation today. First, I'd like to thank everyone for joining us who is currently on, and it's my understanding that this will be recorded. Thank you and welcome to all the future participants who may check in. I hope to do this subject justice. This was a fairly lengthy project, I think, in terms of CERTIP projects. And we've made a lot of significant progress, and I hope to share a lot of that with you today. The title is Atmospheric Plasma Depainting. The background on this project was in response to an open solicitation back in November of 2008 entitled Environmentally Benign Non-Performance or High-Performance, Non-Media Paint Strippers. And in that BAA, there were a number of features that were desirable in terms of a new technology that could potentially replace existing methods of removing paint from various DoD assets. And today I'm going to focus the effort on Navy ships, although our background really is over many other different types of platforms. When we first looked at that statement of need, and you can see that some of those items have question marks versus check marks, we felt that this technology very strongly could easily, immediately resolve about half of the problems, and with a little bit of work, we felt that the remainder of the problems could be solved as well. So the technology seemed very suitable for this particular project, and it started officially in April 2010. We had been working with several folks on several other projects around the country, other DoD assets, aircraft, etc. And so we formed a team along with the university here with a very powerful commercial entity, AP Solutions, run by Pete Yancey, who was a former student of Dr. Cuomo's, and together they spun off a company for commercializing plasma technologies. Additional partners we had were from the Naval Surface Warfare Center in Carter Rock. They were extremely valuable throughout this project. Folks from the Air Force Research Labs in Dayton and also NAVAIR at Cherry Point. So that comprised the team for this project. Technical objectives should follow the statement of need, the desired benefits. Overall objective was to develop atmospheric plasma for the purposes of any DoD asset, although we did focus our effort to make sure that we hit the targets we intended with respect to ship applications. There were many expected benefits of this technology, and they can be grouped into environmental advantages, economical, operational. So the overall approach, when we looked at the work structure that we need to complete, since we had very little background, we approached this in 3 big phases, and each of those phases was further broken down into tasks and subtasks. The initial phase was essentially to gather a lot of background information, specifically with respect to Navy paint, since we were not familiar with those systems or the assets they were used on, or the techniques and technologies that were being used for the Navy. So there were several specific tasks to identify how the plasma was capable of removing the paint in terms of removal rates, the resulting substrate condition after the paint was removed, and then some basic understanding of the plasma system itself. So combining that information together, we moved on to the next phase, knowing that these systems were rather large in size and that we were going to have to scale up the system. We had planned to do to do scale up. And along with that, originally we had talked about some hybrid systems that might be needed to couple to the large area system. Throughout the project, we had so much success that we eventually decided not to pursue any of those hybrid systems, and therefore those particular tasks were canceled. The next phase of the program involved the handling of the waste that was generated and a lot of the environmental and operational features of atmospheric plasma with respect to operation in a naval environment. And finally, putting all that together, grouping plasma technology with the waste remediation systems, we ended up developing and providing what we hope to be a complete atmospheric plasma treatment system for the Navy or other DoD assets. So a lot of the information was knowledge generation. So let me get right to the structures of the paint systems that we ended up choosing since there were so many. In general, there are two basic setups for Navy ships, and they can be grouped as above the waterline, which you see there is as freeboard. And throughout the presentation, I've abbreviated that FB, freeboard. Try to keep that in mind as I go through the presentation. There are a lot of slides, so I intend to try to go pretty quickly since everyone has a copy and an access to this. And if there are some questions, we can handle those as we come up. The second coating system that we looked at was below the waterline. And it was slightly different, obviously, because they have different needs. Thicker systems. Both were applied to marine-type steel, carbon steel. And notice that on the anti-fouling underwater system and both the top coat, freeboard, there are different colors. And there are a number of reasons why colors are used. One is to ensure complete coverage during painting. Another is that with respect to the underwater coating, those are ablative coatings that wear off over time because barnacles and algae tend to gather on the ship. So it gives a visual clue as to what layer one is at in the paint system, and some other reasons that they have the paint colors. For us, from depainting point of view, we were concerned about the composition of each of these different systems in terms of how they would react with the atmospheric plasma. We'll try to talk a little bit about that as we progress. This is a very simplistic setup that we have in our lab, and AP Solutions has a very similar setup, might vary in size and capabilities, but essentially we had a robotic system to manipulate the plasma over the sample, which was placed inside of a reaction chamber or a vacuum debris box that we could collect the waste and manage it appropriately. Over on the right-hand side, you can see the power supply in this case is a very small unit, about the size of a microwave. This is what we initially started with in the program, and I'll explain a little bit as we go how that system and setup changed, if I can. To get our feet wet very early in the project, we knew that if we potentially could somehow get to the very top, or the bottommost layer in this case, right next to the steel, if we could somehow remove the primer, then the rest of the coating would just come off easily. So we thought it was a smart thing to do to look at the primers themselves, and there were several different primers. We wanted to investigate these effects early to see how significant they were so that we can screen out a lot of unknown or not needed variables to look at. And you could see some examples there of the three different systems we looked at. And this slide here just presents an overall example of the type of data that we might generate when we removed paint from a panel. So we would measure the mass and compare those. And you can see there are some subtle differences even just with the primer systems. And fundamentally, those relate to the composition of the materials. I think anyone who's familiar with military systems knows that there's a number of different ways to specify products and processes. You can do it based on a formulation or the need. You can formulate a specification based on the performance needed of that system or some of the details for the system. So some of those differences are just related to composition of the material. We decided to just down select. The most available paint we had ready access to was international paint, so we just went with that. Once we did a lot of our initial background work, we set up to accomplish phase one, which was to investigate the removal rates. And we used several different types of experimental designs over really only those two types of samples, but we looked at a number of different relationships that we could control in the plasma removal system, and you see those there. One of the more interesting ones, we looked at the effect of temperature. I mean, after all, a ship could be almost in near freezing conditions at the dry dock or around there, and then on a hot summer day it might be over, very hot. So we wanted to see if there was any effect of temperature, in addition to a lot of the other variables that I have there. So I'm not going to spend a lot of time on design of experiments, but this is just one example of a typical result that we would get. In this case, we were looking at the effect of the angle that the plasma was impinging on the surface. And I'm going to point to one specific example here. Now, the plasma was moving in this direction. The arrow's backwards on this. And in this case, it's effectively pushing material off as it's sweeping. The idea was there, if we could undercut the coating and lift it off, we could push the entire coating off in one sweep. As opposed to that, if we had a negative angle, and I kind of call this a pull, some of the material as it was removed was redepositing. Actually, it would be these ones down here. You can see that as the plasma was moving in this direction, some of the material would redeposit back on the surface. So it was just something to take into consideration for later in the project. Here's an example of the typical response grids that we get. We use commercial software from a company called SAS, if anybody's heard of them. The product name is called JUMP, where you can do a lot of statistical analysis and design of experiments. And I just wanted to show quickly two examples. A very simple one. In some cases, the relationship, for example, between flow and the angle of the plasma was fairly linear. But in other cases, the results were nonlinear, and there could be an optimal point here between the speed and the height of the plasma that would be beneficial for plasma removal. So we took this information one step further. There's an optimizing program within the JUMP software that allows one to essentially grab, for example, these bars. I can't do this live because it's not software. And we could say, well, what if we wanted to make the paint remove a little faster? We could pull this up, and it would make adjustments into speed and flow and height to give us a direction in terms of what order of magnitude and direction we should pursue to affect the relationship we were. And we weren't always interested in just removing the paint as fast as we want. We also wanted a very clean surface. We didn't want the surface to be overly treated. For example, then you'd be wasting the plasma, because if you've already removed the paint, why continue to go over that surface? All right, let me go to the next slide here. So that in summary, in the first phase of the work, and it didn't take us too long to get this far, but we knew that plasma was going to be suitable for this technology. Here's two examples of the freeboard system before it's been depainted and after, and then the anti-fouling before and after. So plasma works. The next question is, how well? Well, what does it mean? How well does it work? Well, let's take a look at a couple of different variables. The first one here is removal rate. Now, I have to say at the outset that removal rate is a pretty complicated variable to try to understand what it means. From a contractor's point of view, it's real simple. They have a ship that has to be depainted. They know the surface area. They've got to take it off, and they have to do it in a specific amount of time. From our point of view, we have to deal with a number of different variables, such as different paint thickness, different paint types, the environmental conditions at the time, location of where this paint is, accessibility. So all of these different factors will ultimately roll up into what is referred to as removal rate. And there's a tendency to focus only on that one number and say, well, it doesn't meet the removal rate. Well, there are a lot of other factors considered, not including environmental concerns. How well is the operator treated, or what kind of protective gear do they have to wear, and many other things like that. So the first metric that we chose as a common denominator was the mass, because after all, that's what we are removing, or that's what the plasma is removing. So we did a theoretical calculation, and we looked at how much paint was on which type of a ship system that you could see here, and we added that up, and we compared. The way we got these numbers was a combination of different methods. Both in the literature, we talked to different contractors, although contractors are very skittish about giving their numbers because it affects their bidding price. So we came up with some general numbers that we used in terms of the time it would take grip blasting to remove that. We used all the information from our design of experiments, and here's one example. Let's see. Well, it's about a half a gram a second is the number that we used in this calculation. And compared that to grip blasting, and we come down to say that, well, we need something like 8 plasma nozzles to get us there. Now, this was good news from our point of view. I was a little bit skeptical. I think that number seems a little bit low, but it's a starting point. It at least puts us in the ball game. Okay, another way we did this calculation on the next slide is we converted mass to area. And there are some assumptions that one has to use when you do that. Each of these paints have different thicknesses. They each have different compositions. They have different levels of fillers in them. They have different, a ship that may be out for 10 or 15 years may have additional material embedded in it, although ships typically are pressure washed when they come in before their paint is removed. But anyway, doing this calculation again, looking on some level of around 270 square foot per man per hour to remove paint, we came up with a number of something like 14 nozzles that we would need. Again, that seemed manageable for us. So for the purposes of our work throughout here, we used this number of 50 square feet per hour as a guide, as a target, and we felt if we met that in the laboratory, it would be pretty easily to meet in the next phase of the work. So another question about how well does plasma work relates to the condition of the surface that's left after one is finished. Obviously, when a surface is grip blasted, they want to go ahead and repaint right away. They don't desire any other technique or tool to have to clean it up before you repaint. Same thing here with plasma. So I've shown a few examples of what these surfaces visually look like. The first panel here is as received steel from the manufacturer, and anyone who's familiar with steel knows that these surfaces have a lot of loosely bound oxides in addition to grease, and other types of particles that have to be removed. And that's what the effective grip blasting does. One, it removes a lot of those contaminants, and it also imparts a surface profile to the surface that we'll talk a little bit more about as we go on. Well, here's an example of grip blasting, and I think everyone on here can notice that it looks like it's somewhere in between the two. So what is the visual difference? Why do we have a seemingly darker surface here as opposed to a grip blast? Well, to help understand that, we have to look at the chemistry of what iron, or more specifically iron oxides. After all, we're looking at the surface of the iron that has been exposed at some point. Now, in the case of grip blasting, there are a lot of different types of media that are used, but all of them essentially wear through the surface of whatever's on the steel until they essentially get down to base metal. And now we're down to iron 0. Well, that iron is going to want to reoxidize, especially in an atmospheric environment, in a Navy yard with salts, etc. And very commonly, water is involved, and I don't have the equations here for the formation of rust, but in the presence of water, iron will form various different oxides, especially hydrous types of oxides that are fairly porous, that are weakly bound, that are not desirable for painting. Now, in the case of plasma, I'm going to come back to this and show more data, but we have found that the oxides that are formed with respect to the plasma, because the plasma is in itself an oxidizing environment, tends to form very stable forms of iron oxide in magnetite or hematite, iron +2, iron +3, up to the full oxidation state. So one can easily see that we're in between these two types of oxides in terms of color. All right, I have some additional information on that, but before I come back to that, I wanted to talk a little bit about heat, because everyone that approaches us about plasma technology, they're either familiar with extraterrestrial plasmas that are very hot, the sun, solar coronas, or plasma cuttings. Not all plasmas are created equal, and the type of plasma that we're using is what's referred to as a low temperature plasma. It's more towards room temperature. So it's a highly energetic, chemically reactive plasma without the excitation of the ions, which gives rise to high temperatures. So in this particular example, we placed a series of thermocouples to demonstrate this at various positions, which are demonstrated here at 0 millimeters, 50, 100, 75, 100, and then all the way to the end. And then rastered the plasma across this surface to affect paint removal. And here's a thermal image of that at the beginning and the end. Here's a real photograph of the plasma in action. And then the thermocouple traces at each one of these positions. And notice that at each one, the temperature will build, it will maximize, and then it will drop. Clearly, as the plasma rasters over the surface, there's heat input, but then it readily moves off. And so there's essentially a heat wave that moves through the surface. Notice that the temperature really never gets much hotter than, we use 200 C as our absolute top temperature, which is roughly 400 F, close to annealing temperatures of steel in this case. So we're designing our system specifically for this type of a substrate, which is different from aluminum or composites, okay? Because and I don't want to spend a lot of time on this slide because it's very complicated, but because this heat issue was so important, especially on the inside of the ship, and if we were going to use plasma around other types of operations or in the inside enclosed spaces, we really had to understand heat input. We took advantage of another project that we had at the time that was with electron beam melting for additive manufacturing. We had a graduate student who had developed, based on sound scientific principles, Fourier heat transfer law, the heat input as a function of various parameters. And using a Gaussian distribution, we modeled that with the example that I just showed you as one. When we first ran the profile, we found that the measurements did not exactly match what we were attempting to achieve. And it wasn't until we had to force a second term into the model for induced convection that we got the same results theoretically that we achieved experimentally. That was a very important discovery for us because we had originally thought we might need to use some hybrid technologies if necessary to aid in paint removal. So what this demonstrates is if necessary, upon scale up, there could be alternative systems added that will help us resolve any type of thermal issue that may be present or not. Okay, coming back to the chemistry. Hopefully you're familiar with X-ray photoelectron spectroscopy. This is a very surface-sensitive technique. It only looks at something like 50 to 100 angstroms of a surface here. So we're looking at, on the order of 10 or 20 chemical bonds. Very, very surface-sensitive. This first spectra was obtained from an anti-fouling panel that was depainted by grip blasting. And notice here that there still was a fairly high concentration of carbon on the surface and a fairly low concentration of iron. And now I don't know if this particular sample was pretty typical of a grip blasted sample that one gets. And notice in the oxygen region that the contributions due to organic, or shall I say oxygen bonded to carbon, is fairly high, or at least equal to the ratio of oxygen bonded to the metal. When looking at the iron spectrum, there's a combination of peaks from ionized iron, iron plus 2, iron plus 3, and also, interestingly, a peak due to iron 0. Well, this goes back to what I was saying earlier about the effect of grit blasting a surface going all the way down to metallic iron and then subsequently an oxide growing. We also saw in this sample residue, some from the paint itself and some from the grit that was used to affect the blasting. So if we think about this process, we've got a highly energetic kinetic media impacting a surface, and one can envision that low areas, say the valleys, the grit may not be able to reach into those areas to affect complete removal, so there's probably always going to be a little bit of paint remaining. with grip blasting. That's not necessarily always the case, but certainly in this case, it appears that there's some paint remaining. Well, let's compare that to, oops, went too far, sorry. Let me go back here. Let me go to this one. This is the same type of a sample, anti-fouling paint, but in this case, the paint was removed with plasma. Well, immediately notice that there's a lot of fairly high intense peaks up in this region. Most of those are related to iron, and if we look at the atomic concentrations, about half the amount of carbon. Now, I have to say that with X-ray photoelectron spectroscopy and all the work that I've always done, from atmospheric exposed samples, I've never seen below about 15% carbon. And the reason for that is there's always adventitious carbon that gets absorbed onto a surface, especially a metallic, highly energetic surface for XPS. But if we look at the amount of iron and oxygen, it's pretty clear that there's, in this case, much less paint left on the sample than there was in the other case. And that is confirmed by looking at the oxygen region, wherein here the oxygen bound to carbon is much, much less in relation to the oxygen bound to the metal. And then if we look at the iron surface, well, in this case, there's no observable peak due to iron oxide, to the metallic iron. It all appears to be oxidized. So this is giving us the first indication of the thickness that oxide may be. It has to be at least 100 angstroms or so, because we're not seeing metallic iron on this sample. I guess that's all I want to talk about on that. Let's see. We used another technique which probes a little bit deeper into the surface, X-rays, which could be on the order of the, closer to half a micron or so in depth of penetration. And if you're familiar with how they work, we used a technique called glazing angle because we were interested in the oxide or the very uppermost surface that we could get to. And this particular sample was the grip blasted sample, and it was primarily iron with really very little trace of oxide on it. Now, if the oxide were on the order of 50 angstroms, like we saw in XPS, it might not be possible to detect that in X-ray diffraction. Well, this was interesting compared to plasma sample. First of all, the counts are much less, so there's a lot more noise here. But the primary species that we found here were oxides of iron with traces of iron deeper into the surface. So this gave us further evidence that the plasma was creating an oxide on the surface, and that makes sense. Now, from our point of view, that was good news because we felt that these oxides were very stable and controllable, and without metallic iron there, the potential for this surface to rust in the future would be minimized. So we deemed this as a good result in terms of a protective coating that was formed on the surface. Additional work we did was to look at both painted, depainted, repainted, depainted a second time surface. This particular slide shows scanning electron micrographs of various steel surfaces, pretty simple ones. This is the as-received mill scale that we saw earlier that was a dark gray in color. And notice that there's a lot of high topography or a lot of strong morphology here. It's not smooth by any means. There's also free particles from the mill scale as it's formed. And then once this surface is grip blasted, it becomes more uniform, if that's fair to say. It's still fairly random in terms of its surface texture. One of the questions that was raised in the statement of need was, does the plasma alter the topography? And there are reasons for that roughness: mechanical interlocking, increasing the surface area for bonding, ensuring that the paint longevity will last. Well, these surfaces were treated to plasma, and visually, both in SEM and optical, and in a couple of other techniques that we used, we couldn't find any physical changes with respect to the topography. And that makes a lot of sense too. Once an oxide is formed, well, then what's next for the plasma? There's no more work for the plasma to do, and so the surface essentially self-passivates, if you think about it that way. So to back up that data, we did profilometry, optical profilometry, and here's the result over a number of different samples, whether they were plasma, freeboard, anti-fouling, grip blasted. We even took some of those grip blasted samples and then plasma treated them to effect removal of the rest of the paint. In all of the cases, the profiles were around 50 microns, which makes sense. It's not on this slide, but the grit that was used was, it's a 5 millimeter grit intended to achieve a surface profile of 2 mils in terms of roughness, and that's 50 microns. So this gives us a couple of really interesting data points. One, all of these surfaces had roughly the same type of roughness, and two, the profile is what is desirable for the military application. All right, so we moved on. Now, after laboratory work, we decided to do some field work, and this piece of work was rather extensive. A lot of coupons, a lot of time, a lot of different testing, a lot of effort went into this. These are the typical types of tests that would be used to certify or qualify or to write a specification for a process to be used. This work was, we were interested in the stability of that oxide surface over time. So we produced two different types of samples. The first sample, once they were plasma depainted, they were primed same day. And the mil spec on grip blasting is you have to repaint within 4 hours, otherwise the surface has to be re-inspected and recertified. And the reason for that in a grip blasting environment in the marine is a lot of salts and water can alter that surface in 4 hours before it's repainted. So we let those samples sit. We did another set where they were stripped and then they're stored at least a week. Then we shipped them to the contractor where they sat for at least another week before the first set of primer was even put onto the surface. And then the final set was the control set of grip blasting. And all of these samples were subjected to lots of different kinds of testing, environmental and analytical. So the first result I'm showing here, this was the first thing we wanted to see. Was there, and now these samples, by the way, after they were depainted, they were repainted. Okay, so let's try to keep up here. Let me explain these. We had steel that was originally grip blasted and painted. Then they were depainted, either with grip blasting again or with plasma, and then they were finally repainted, similar to what one would do in the field. So these are optical micrographs taken from cross-sections showing the paint-steel interface, and they were etched with nitol to bring out the grain boundaries of the steel. And notice, based on the scale, where's the scale? 40 micron here. So again, the roughness of these surfaces is on the order of 50 microns in scale. We're looking for an oxide that is less than a micron. And it's pretty tough to see that in these. I think we'd have to do some pretty fancy techniques to really look for that. But the point of these two samples is that essentially, and on all the ones that we looked at, we couldn't find any differences, whether it was grip blasted or plasma treated. So let's move on to some of the performance tests and these are common if you're familiar with these. The first one, and notice primer only, the weak link in the system, typical of a pull-off adhesion, whether this is done wet or dry, to determine if there's a good bond of the primer to the surface. That's the most important thing, otherwise the whole system's going to fall off. The numbers ranged anywhere from about 3,000 to 5,000 psi. We did see some variation, but it was pretty normal scatter for the statistics. On all of the samples that we had, the mode of failure was within the top coat, and that told us that we had really good adhesion dry before any kind of testing whatsoever. So then we went on to some of the other tests. Of course, this was all done at the same time. The ubiquitous and all-knowing B117 salt fog that everyone's familiar with. We ran that for 3,000 hours. The 1,000 hours is the standard. No significant differences. Moving on.
Is there a question there?
Oh, all right, no question. Another very significant test that we undertook, which is as close as we could get to the real world, is alternative immersion in seawater. So this is where the panels, I forget the cycle, it might be twice a day. The panels are dipped in seawater and then pulled out, similar to what a ship might see in the ocean. We did both, of course, anti-fouling and freeboard, and all of the ones above. That samples were scribed or unscribed, and the bottom line is, even after 4 months, there was no problem with any of these samples. We decided to let them cook even longer because we had already paid for this testing. And at the end of the tests, there were absolutely no problems. Okay, if any of the tests, this is my personal opinion or professional opinion, if any of the tests would have shown some problem with that oxide at the surface, I felt that cathodic delamination would have done so. And the reason for that is it's an electrochemical test, which is going to tend to find weaknesses in that oxide layer. And in fact, we didn't find any of those problems. All right, I'm going to switch gears now and talk a little bit about plasma. And I'm running just a little bit behind, so I'm going to try to go a little faster. We looked at different types of plasma systems. Of course, the one that we used was a commercial system with proprietary components that we really couldn't divulge or look at any of the fine chemistry of the plasma itself. So we designed a model that we could vary all of the components to it to study a plasma system. And this will give you an idea of the type of plasmas that we looked at, many different types. Not all in great detail. Some we only looked at briefly, while as others we looked at more depth. We were interested in the energy density of that plasma. And one of the ways that we could do that, plasmas are generated through electricity, so we measured the waveforms of these plasmas, the power going into the system, and looked at the resultant properties of those plasmas. In addition, we did fluid flow modeling, so to try to understand how the plasma was being generated and all the effects of the flow. One of the interesting discoveries we made was similar to a jet engine or the space shuttle taking off. When you have supersonic flow through a nozzle, when you have compression and decompression, one can generate Mach disks or concentration zones in the plume of the exhaust. And that was a very interesting discovery because we had noticed previously an effect of the height, or shall I say the distance away from the nozzle in terms of its etch rate. So there could be some sweet spots here to take advantage of. So that was very important to understand. Another technique that we use to look at plasmas to determine their chemistry is the emission spectra. And notice right away the ubiquitous, well, the very important 7777, which is referred to atomic oxygen. Highly oxidative, in terms of a plasma, long life species, very important for affecting oxidation of paint systems. In addition to that, a number of other active species of oxygen and nitrogen, because after all we are using air, and a little bit of nitric oxide in these spectra. I won't go into a lot of detail, but we had a PhD student go into great depth into examining the morphology with respect to the position of the plasma and its chemistry to try to find what the difference is and to understand the type of plasmas that we were dealing with. And that's in the thesis, which is in the publications at the end. I'm not going to dwell on this slide either, but we looked at one other type of plasma system Dr. Shannon looked at. This was not showing great promise at the time for paint removal, although it had some advantages. So we made a very conscious and very easy decision, actually, to move forward with scale-up of a system that we had been looking, maybe close to a decade, maybe not quite that long, but a well-developed system, well-characterized and understood. So instead of looking at a single nozzle, the concept for scale-up was to start to modular or to add those together and to make a module. And the way that was done was to look at 4 pen systems. I refer to each one of these as a pen from top to bottom. Then, of course, the nozzle itself, and then the module itself. So let me go show some of these results. We found out that the power supply we had to do this work was, because it was already built, wasn't satisfactory to power all nozzles at the same time. So while we were working on a new power supply, we looked at the effects of multi-nozzles, one or two, for this system. One of the interesting things in this case for linear rastering, which was one of the methods we used to look at paint removal, was the angle that would be used, because that would determine the spacing between plasmas to raster over a surface. So this is a pretty typical example of what that would look like, cleaned all the way down to the single metal and a single pass. Notice a little bit of difference here between the oxidation state, or the, shall we say, the oxide layer thickness here. I also want to point out what's interesting: red, gray, maybe red, black, red. So each layer of the paint system is visible in here, and a little bit of overspray. So by carefully controlling how these nozzles are configured together, we can have them work synergistically so that some of that overspray, instead of redepositing, would be removed by another nozzle. And this graph here shows an example of that. For example, if there's just a single nozzle, this was typical result. But by using multiple nozzles and the angle, the proximity that they were to each other, looks like there was if they get close enough together, one nozzle could effectively help the other nozzle remove paint. Moving along to the next phase. So this is we're well into phase 2 of the project now, to build a high power supply for plasma that was capable of many new features. And I really have to compliment AP Solutions on doing a fantastic job in building this. I don't know if I have time to look at all the advantages, but suffice it to say that this new system has proven to be very robust. The footprint is exactly the same as the old one. However, it could easily be reduced 2/3 in size by compressing some of the components. In addition to that, some of the new advances in high power circuitry would make these types of systems very small, or potentially very small. Now this particular system can power at least 8, I think up to 16 nozzles all by itself, to provide an example of the size of the system. Here's one of the 4 nozzle systems that were built first. So you could build 1 and then 2 and then replicate as many as you want, gang them together whatever size, build as many different power supplies as needed, or maybe make the power supplies even bigger. So we used a logical progression in our work and scale up. Start small, make it bigger, make it bigger. Here's an example of that 4 nozzle system by itself, with the new power supply. Immediately saw a 46% improvement in terms of removal rate of the paint, which was a very good discovery. And I'm looking at my time here, 1:23. We're still running a little slow, a little behind. Moving ahead, here's where we ended up in the project with 8 nozzles, but this could easily be replicated to whatever number one desires. Some slight differences in the way that the 8 nozzle is rastered over the surface because of the geometry. I want to show one example here of the 2 extremes, where the 2 modules are at 90 degrees versus at 0 degrees, a single pass. Clearly these aren't ideal, but that's what you get in a single pass. This is much better. I think everyone agree, and this is what we're after, and that's what we achieved upon scale up. Now, the next slide is very simplistic summary of the trend that we observe, increasing the number of nozzles up to our targeted removal rate of 50 square feet an hour. So we were really close. We're right around 10, 11 nozzles to get us to where we needed for 50. But of course, this is just, a very rough sketch, but it should give us an idea of scale up in the future. Just pick a number. How big do we want the system to get? It's very simple. You just gang them together and make as many as you want. You can make 2 times 8. You can make 4 times 16. You could.
Not much bigger than your computer.
Right. And overall, I don't know if you got a feeling for how big the size of these. It's about the size of a toaster. easily manipulated by an individual with one hand. The weight, very low weight, and we're only using about 100 psi or so pressure, so low pressure airflow. Okay, with the remaining time I got, I want to get into the waste and the integration. Another theoretical calculation we did was to identify how much of the paint would be converted into solid left over from the inorganic fillers, and how much would be converted to gases, in particular CO2, under the assumption that we have 100% conversion of the paint to CO2 and water, some assumptions about the filler content. When we ran this calculation and compared it to how much CO2 is produced by one automobile in a year to remove the paint from an entire ship, it's really insignificant overall when you think about the amount of gas. And in this case, the amount of solids, we're taking the original mass and reducing it 26%, so we have a decrease in the solids. Now, this was a theoretical calculation, but we also did it experimentally. So we had an enclosed chamber, rastered the plasma over the surface, weighed it before and after, both freeboard and anti-fouling, measured the mass lost on the coupon. The rest had to go somewhere. The entire chamber was scrubbed to see what could be collected and what could not be collected. And very interesting, much higher concentrations, and this makes more sense. Somewhere on the order of 45 to 60% of the original paint mass is converted to gas. So I'm going to skip to this slide and get right to it. This is a pretty good summary. If one is using grip blasting to remove paint, this is the volume of material that you're going to have before and or after the painting. With a plasma, we don't need any of that grit, and it's a very small fraction of material that needs to be recovered. So let me go back to this real quickly. This is SEM. Yeah, this is SEM of some of those particles. The bottom line is the material is primarily, after plasma treatment, the waste ejecta is the inorganic fillers that were in the paint to begin with some of the paint residue depending on how quickly the plasma was rastered over the surface, etc. All right, so what about the gas composition then? Well, this is an analog grab sample which identifies all of the gases in the exhaust. And here we see, well, of course, primarily it's air, nitrogen and oxygen, but here's water and carbon dioxide and a little bit of nitric oxide, which we expected based on the OES. Much more interesting experiment is to run the plasma over time. Let me explain this graph briefly because this is very important. We started at time 0 and monitored each of these gases as a function of time. So right here at 1 minute, the plasma was turned on, but it was in free flow mode, just exposed to the air, running. And of course, there's the nitric oxide that's generated. And we could talk about the effects of nitric oxide later, and then at about 2 minutes, the plasma is turned on. And in this case, it's rastered over the surface back and forth, back and forth. So it spends some time on the paint and some time not on the paint. And that's why there's a sawtooth pattern here. Well, here's the CO2, here's the water, here's carbon, which could either be from the paint or more likely probably from breakdown products of the CO2, and some NO2 as well. But remember, this is on a log scale, so each of these increments is a factor of 10. So if we really look at the partial pressures involved, the amount of gases, well, let me not dwell on that, but the conclusion is basically that the paint is being converted to carbon dioxide, water, and oxides of nitrogen. If you think about it, as long as the plasma is exposed to the paint, it's going to react with the paint. But if there's no paint there, it's still highly energetic, and this atomic oxygen coming out of the plasma is going to react with something, reacts with the nitrogen that's in the air. That's a simple problem to resolve. Commercially, you just put a switch on, Plasma comes on when it's on the surface. When you take it off, you turn it off. We developed a very simplistic mechanism for how the plasma removes the paint and the resulting products. That's summarized there. We looked at some of the environmental hazards, and this is really the very last phase of the work, was to look at the sound. Normally one would be, 4 feet away from the source? Okay, it's close to grip blasting. There is some noise with the plasma, but this is a free-flowing plasma. This wasn't even enclosed in a shroud yet. Electromotive EMF stray, because we're using radio frequency to excite the plasma. Well, compared to a cell phone, your Wi-Fi router at home, or a microwave oven, we're not even close in terms of any type of potential interference. Similar, a lot of people are concerned about UV exposure with plasmas do generate some UV. For comparison, a fluorescent bulb, which also generates UV light, this is a commercial bulb. We're concerned with frequencies below 400. This is where we get into the UVA, BC range. Even a fluorescent bulb, bare, there's some excitation. Of course, with safety glasses, that's completely removed. Same thing with a plasma. One does need to wear safety glasses. Be a good idea. Okay, the final step in the project was to integrate the plasma technology with a waste integration system, and that's what you see in this slide. Give an idea of the size of this thing. This coupon is 6 inches by 12 inches in size, and running with a particle detector during depainting, there was in the first shot prototype right out of the box, 85% reduction in the amount of particles that were lost to the system. All right, not spending a lot of time on the shipyard visit slide because we're coming to the end here, but for anyone involved in any type of project like this, absolutely invaluable to make a visit to where this work is being done. Far too many aspects of plasma depainting were important and will continue to be important in the design of the system for field use. This is a budget slide which shows a breakdown at the end of the project in terms of the funds used overall. All right, let me get into some of these conclusions. From each of the phases, we've learned that atmospheric plasma does indeed remove paint. It removes it at rates that can be comparable to grip blasting. One of the aspects we'd love to look at would be the economic aspects in respect to the environment. How much cost could be saved because of the environmental attributes of plasma, and that would determine how big it has to be. Now, the surface, as tested both analytically and in environmental performance test, was satisfactory for repainting. The composition of the plasma was highly energetic species of oxygen and nitrogen. We looked at the ejected material, both the solids and the gases, solid type and quantity, basically inorganic filters left in the paint from the paint, the gases primarily carbon dioxide and water vapor, some oxides of nitrogen depending on how the system was run. And the bottom line is we feel that atmospheric plasma is a very versatile tool. Now, would it be a shame to just let this work sit on a shelf? So what would we need to transfer a lot of this technology? First is to make sure that the knowledge is transferred to users and approvers. Now, what I mean by that is one of the things we discovered in the shipyard visit, like most places, is the work is often contracted out and bid, and the contractor is going to do what they need to do to get the job done. And then the sponsor has to be happy that the work is done. So these two entities really need to work together to ensure that the technology is suitable and economically feasible. There's a lot of modifications that are going to be needed for field use depending on the size, whether it's a small area system, which we feel is ready to go with minor modifications of attachments, to how big the system needs to be. And some regulatory review, once everything is set up, of course, to confirm or to make additional measurements on a lot of the things that we've already measured. The cost benefits analysis would be perfect to determine how big this system needs to be and whether or not it needs to be automated or can be manually operated. And finally, there are many other applications that we didn't discuss in this talk for how atmospheric plasma can be used, both from the point of view of removing sealants and coatings and also remediation of biological, chemical, or other types of organic contamination. So with additional funding, right now we don't have any funding or steps necessary for commercialization, but we really feel this technology is ready for the next step. So with that, I'd like to thank everyone for your patience, and we're still okay. I think we have time for a few questions if there are any.
Thank you, Stephen. Very, very nice presentation. I'm going to start off, and then I'm going to pass it on pretty quickly. I hope we have time for a few more questions than just mine. Did you do any analysis of the solids, the ejecta?
Yes. One of the slides I showed in this presentation was the SEM. We did.
I mean, like chemical analysis, something like measuring the organics, extracting organics, something like that.
Well, two things. One, we did some XPS on those.
Okay.
And of course, XPS, it doesn't tell you whether you have amines or epoxies or some type of functional. It just basically tells you have organic oxygen type materials. The SEM EDAX scans, again, that doesn't give you fine chemistry. I think my question really revolves around the breakdown of the paint. So I'm assuming that the plasma is not oxidizing everything and taking everything from this polymer to CO2 and CO and H2O. Well, I think I'd agree with you in terms of the material, the ejecta, what we refer to as the ejecta. If you do this to completion, yes, we end up only with inorganic fillers. But you're right. Some of the paint will be clinging to those particles. Some of that paint, although we haven't seen a lot of it in its native form, it tends to become a little tacky. Okay?
Yeah, so that's tars and things like that.
Right. Now, we address that by a series of filtration. The first step filtration would be a disposable filter that you collect really large particles. And then you step down to smaller and smaller filters going to cyclonic filtration. I think the best way to answer your question is after many years of running these plasmas and paint and collecting everything that was deposited inside of all of the systems, I was just in the lab the other day. I took some soap and water and wiped it over the surface, and it came right off. So whatever the chemical composition is left, I would call it inert. It's easy to deal with.
We don't know, but that's what it seems.
Okay, inert has a few different meanings.
Right.
Yeah.
So the other question I had to do with the fact that this is an oxidizing environment. And as you proceed and start thinking about depainting aluminum and composites and aircraft maybe, that oxidizing environment might lead to turning things into other things like chrome 3 into chrome 6. And have you been considering that?
Let me take each one of those questions in turn. Any metal surface, in general, metals tend to oxidize. And they form an oxide in the environment that they're exposed to. Yes, aluminum does oxidize. Now, we've actually done some work with different types of plasma in terms of aluminum to actually create surfaces, clad surfaces on there. One does not have to use an oxidizing plasma for everything. We're trying to remove paint. If one is trying to convert a coating, you can use a reducing plasma. Now, you're right, though. If you use an oxidizing plasma, it will oxidize the surface. In the terms of an epoxy graphite composite, yes, it oxidizes the epoxy. When it gets to the graphite fiber, it stops.
We had a program with Cherry Point for chrome 6, and we've actually reduced the oxide down to the chrome 3.
Okay.
All right. So we've done some of that work, not extensively,
Right.
Robert.
Yeah, this was a far-reaching question, I thought, anyway. But that's good. I didn't recognize that was possible. Good. I want to open it up. I don't want to control all of this. I want to ask if there's any other questions around the, I was going to say room, but whatever we have here.
Ethan.
Hi, this is Bruce Holden. I wanted to ask, did you consider, instead of using air, using oxygen? And, is there no advantage, or, just your comments on that?
That is an excellent question. And the reason is the input gas will determine the output plasma. Yes, we have done experiments in adjusting the oxygen concentration. In fact, on this particular project, in the final report, we used 100% nitrogen only as the input gas, and then slowly added oxygen in a ratio to look at the effects of that. We did not see huge differences dependent on the concentration of the oxygen. Not exactly sure the reason, but probably because the type of plasma that we were using was fairly localized, so it reached an energy level that was supplied to it, and perhaps no more. We saw slight variations in etch rates without doing a lot of really quantitative work. Now, if one would go to an inert gas, such as helium or any of the noble gases, argon, xenon, you're not going to see this type of ionizing or oxidizing effect. In fact, in the industry, there's many other gases, SF6 that are used, silanes if you want to put some kind of a silica coating down on a surface. So your question is an excellent one, because you can control that plasma environment by the gases that are used and the way that the energy is excited.
Yeah, but for our interest, it looked like there was no great effect, and therefore the most reasonable thing to do commercially would be to use air. And that's from a compressor. Everything is available to you. There's compressors are at the bases, so we thought that would be naturally the gas to use. But we did explore the others.
Yeah, it's a good question. Anything else?
It's Hertel from NAVSEA Carderock. Yeah, there's definitely safety issues with using oxygen, right? But my question was, I have a couple, but I'll just try to keep it short. As far as what you mentioned earlier on about this comparison of removal rates, I think what you were trying to get at was the difference between removal rate and production rate. Often that's the big deal. That's what the contractor looks at. That's what the shipyard's looking at, the production rate. So, your equipment setup, complexity, safety, PPE, all that other stuff comes into play to end up, getting a production rate. The equivalent 50 square feet per hour, I heard you mention as far as equivalent. Just so I'm clear, is that what you think you can achieve with reasonable, with a reasonable level of technology, or is that just? I guess it depends on how big you want to make the head and how many nozzles you'll have on the head. But I mean, is that sort of the general findings from your research to this time, that you think practically you could put something together to get 50 square feet per hour? Because I think with typical blasting, you're getting that on probably the low end. But if you get into more complex areas, you can get up to, flat areas you can get up to 120, maybe a little bit more. But I don't think it's typical. And the other thing, as far as profile, I saw, it's interesting all the work you've done to see that, even though you don't have unequivocal proof of whether or not the changes you make to the surface are actually more protective or not, they don't seem to be detrimental at all. But I guess, did you also I'm sorry I'm asking you tons of things at once, but the grit you used, the aluminum oxide, was that consistently used for all testing, the same type of grit? Is it commercial grit? It wasn't garnet? This is what typically, the grit you used in your experimentation, is that typically used to blast the hulls?
All right, let me take your first question with respect to production rate. The 50 square foot was a minimum target.
Okay.
And we achieved that today. We have a lot more data that shows it in better format than I put in today with 8 nozzles. Okay, 50 square feet is not a problem with 8 nozzles. In order to scale up, it's a matter of just ganging those modules together. We think that's something very simple to do to reach whatever rate. Certainly on a large flat surface area, we had a talk about getting some 10-foot by 20-foot panels during this talk and saying, well, should we do that? Should we go do a demonstration?
I think a principle that we had early on was modular design. And as we graduated from the 1 to 2 to 4 to 8, we saw that we could gang that 8 into another set of 8 and another set of 8. So you could have a square area which is probably a little bit larger than the size of a large laptop, and actually have 32 nozzles. So we saw modular was really key to the kinds of things that we did, and also that would follow the power supplies that were capable of running each of these modules. So I think conceptually that the scale-up looked very feasible.
The second question related to the stability of the surface after plasma treatment. Believe me when I say we put a lot of thinking into that. We realized that to really answer that question would probably be a whole nother PhD thesis. So we did what we felt was reasonable. I would love to really do a lot of different, we've tried to just do some simple things like let samples sit around in the lab, put water in them, and come back a week later. Some of these samples have been sitting around now for years, and we don't see much rusting or oxidation at all. You know, it's not quantitative, and it may not answer your question, but I'd love to do that. The final question you had related to the grit. We are absolutely aware of all of the different types of grit. We set down to aluminum oxide, the garnet type of grit. We used, actually there were more than one type of grit, because the first set of panels that we used were done by a contractor. I forget their name right now, but we specified aluminum oxide. We did not use Black Beauty or some of the other lower hardness type materials, but over time we probably did 3, 4, 5, 6 different types of sets at different locations, and we really didn't see that the effect of the grit had anything to do with the results we had at all. Okay, I think those were all the questions.
Okay, great, thanks. And as far as the grit reuse, or the economic calculation, where you have the little rail cars or whatever, I'm estimating that you didn't really consider any grit reuse.
Well, in the case of Black Beauty, they don't reuse the grit. Okay?
Right, but you were using mainly garnet. You were comparing to garnet, right?
Right, and we didn't do any economic calculations because, yeah, you're right. Aluminum oxide is more expensive up front. It's harder, it's sharper, it lasts longer, and they do tend to reuse it. My understanding is they'll use it until it becomes right up to the point of contamination where it may become hazardous waste, because then they have to assume additional costs to dispose of it. So let's say, for example, that a ship comes in with lead paint on it. They're not going to reuse that grit. They're going to need to get rid of it. So part of the economic analysis would have to include a comparison to, you're right, and they're going to have different production rates with the different types of grit as well.
Right. I was just looking at the waste calculation that you did, grit blast, how many kilograms.
To be honest with you, I'm not positive what type of grit it was, but it was single use, how much you use. I mean, the way it's been described to us is, to make it simple, other than rail cars, is a football field that's, 6 to 12 feet high, full of grit. That's how much they have to use to blast an average-sized ship.
Right, yeah. Well, yeah, football fields, yeah, something like knee-high or so, waist, in a basketball court, sort of like near the net or something like that.
Right.
Yeah,
that helps.
Yeah, I just wanted to be clear, because if you're going to present comparisons that, just to make sure that everyone understands. But yeah, I mean, it's clear that you're not using media here, so yeah, that's clear. So
and we didn't do any comparisons to water, because we weren't exactly sure how to address. I mean, water can be cheap, but what do you do if it's contaminated? You have to collect it. So those are some other value-added propositions that why we didn't even begin to look at cost comparisons, because there's too many different factors that have to be weighed. and comparing
Right.
each technology.
Yeah, water jets typically, I mean, the systems now are closed cycle. They can recycle the water. Sometimes they're just pump and dump type systems, and usually they heat the surface up enough where the water basically the residual just flashes right off. But yeah, I mean that really wasn't the purpose of the CERTIP really. So yeah, I mean I don't think I really have anything else. If I think of anything in the next minute or two, I'll ask. Thank you. The last thing, just so I'm clear, because I wasn't here on the whole call, but you still get down to areas that need to have profile applied. I didn't miss anything, right? I mean, you're not your
Yes.
ability. Go ahead.
You're right. You're right. In general, we don't see that. Even with grip blasting, there's going to be areas, for example, around some of the anodes that may have capacitic coatings or that have suffered some damage, or for example, they cut the hull off to replace some of the. They have to re-clean the ballast tank. So, you're right. In a commercial operation, there's always going to be exceptions to everything. Our objective here was try to develop two different types of system. One we referred to as a small area system that could be manually operated. We actually crawled into some of the nooks and crannies, the enclosed spaces, to try to understand the differences between getting inside a ship versus the outside where you're exposed to the air, and what the type of equipment one would need. Another thing we talked about is in certain cases it is certainly possible to add grit, since we're just using compressed air, in with the plasma and do plasma grit blasting. That was one of the concepts of hybrid that we didn't really explore. We really didn't feel we needed to do that, but it could be done.
Yeah, that's interesting. And none of the shipyard conversations you have with the shipyard, they didn't raise anything on CO2, right? Because there was another project on the 6.4 level that was done by the NESD program that they were looking at an alternative cutting gas, magna gas, to use for oxy-fuel alternative for cutting up ships, and CO2 became a concern that actually caused a need to reformulate. But I mean, you're not generating enough there to really be a worry, correct?
The CO2 is only generated during oxidation of the paint, and it's a small amount of paint. And I'd love to talk to you more about that cutting, because there's some other things there. But no, we were more concerned about the oxides of nitrogen that are being produced, to be honest with you, because those have, well, depending on the form, in some cases nitric oxide is good for the humans, and others it's not. It can become a pollutant when it converts to NO2. We don't think the concentrations are that high. In the final report, we made some comment. I loved your comment about recycling with the water. We envision this plasma process to be similar, a closed loop cycle. We made reference to the APAC system, where a lawnmower type head could sweep over a surface, recirculate the air, filter the air. Of course, you're just using compressed air in that case. And then if there is any nuisance gas that becomes an issue upon scale up, one could put in filtration with some catalytic converters to neutralize those oxides if they're a problem. I'm kind of surprised nobody asked about ozone, because a lot of times with plasmas, ozone's generated. We're not in that temperature regime for ozone, so we haven't seen it.
Great, thanks.
Okay.
I want to thank you. You gave a very good talk today, and lots of questions, so I really look forward to seeing how this plays out, because I think there is a future for this technology. So